everyone, thanks for joining today, and in today's video we're going to be discussing virtual screening and the use of machine learning in the detection of protein pockets for virtual screening. And today I'm going to be using a piece of software, it's open source software for virtual screening called PocketVina. So anyone who has done virtual screening before will most likely be aware of AutoDocVina. And PocketVina is a variation that is focused on using GPU acceleration. So PocketVina operates in two key stages. So the first stage is that it predicts potential protein pocket centers using P2Rank, which is a fast and accurate machine learning algorithm that identifies the ligandable regions on the protein's solvent accessible surface. And then once it has detected and ranked those pockets, molecular docking is performed at each predicted pocket center using a variation of AutoDocVina that is optimized for GPU-based virtual screening, and that is known as QuickVina 2 GPU 2.1. So just a little background on here, and I probably suggest for you to go and read the paper on PocketVina, but just some key points as to why you would use QuickVina and hence PocketVina as opposed to, say, AutoDocVina or Glide or Gold. So QuickVina 2 GPU 2.1 is specifically optimized version of the AutoDocVina family that is optimized for high throughput virtual screening and builds on the speed of Vina GPU 2.0 and enhances that speed using a reduced iteration and low complexity BFGS algorithm. And that speeds that to a few tens of milliseconds per dock. So PocketVina also is able to achieve large-scale docking throughput in just a few days for millions of ligands, even when executed on standard and cloud-accessible GPU hardware like the NVIDIA Tesla P40 with 6 gigabytes of VRAM. It performs exhaustive sampling across multiple detected pocket centers using the same ligands using the GPU acceleration, and repeats the optimization for multiple pockets, which results in more rational pose estimates. And in several benchmarks, including PDB Bind 2020, the Aztecs Diverse Set, PoseBusters benchmark set, and DocGen, PocketVina show the highest physically valid success rates for rigid ligand docking compared to both traditional and deep learning based models. So before you begin your docking workflow, the first thing you'll want to do is to change over to a GPU instance in Colab. So you can just go for a basic T4 GPU instance in this case. And then the second thing you're going to want to do is to mount your Google Drive. And that's because when we are installing PocketVina locally and also producing all of our docking files, we're using a large amount of memory. And there's a possibility that the Colab instance will time out and you will lose your results files. So to prevent that, you can mount your Google Drive, and then as the docking pose files are produced, they will be automatically backed up to your Google Drive account, so you won't lose them. And then once you've mounted your Google Drive, you should see a message confirming that, and you should be able to look in the content and drive folder and find your Google Drive. Then in the second step, you'll want to perform the initial setup and install the dependencies. So that will install Boost libraries and Java 17 and also clone PocketVina from the GitHub repository. And once that is complete, then you will want to install the OpenCL dependencies and create an ICD registry for NVIDIA and check the GPU status. Then you want to set the environment variables and check the executable, so make PocketVina GPU executable and just verify the installations and any permissions for the programs. And then last of all, you're going to actually build and install PocketVina. So we've downloaded it from the GitHub and we're actually going to install it via Colab. And this will take about 20 minutes. It's obviously a large file and has lots of files as part of PocketVina. So this will take about 20 minutes to install. So grab a coffee, take a break, and wait for PocketVina to install. And then once PocketVina is installed, you're going to want to update the relative paths to absolute paths. And you are going to set the output directory for your ligand files as your Google Drive, so that your ligand files go straight into your Google Drive once they're produced. And now if you go into the PocketVina folder and go into the example subdirectory, you will see two text files named ligands and protein files, and also a proteins folder. If you go into the protein files text file, you will see the paths to two PDB files, which are examples downloaded with the program itself. In the ligands file, you will see ligands in the format of molecule name and smiles. So you'll have molecule 1, comma, smiles. And if you have watched the combinatorial library building video, then you'll remember that we created a text file in this exact format. However, except for molecule name, we had the zinc ID. However, that's perfectly acceptable for PocketVina to use. So instead of having just molecule name, we can have the zinc ID of the reagent to be able to track back and see where the reagents for that molecule came from. And now what we're going to do is we're going to download the PDB file from GitHub, in this case PDB ID 5RMM, and we're going to replace the paths in the protein text file to our new PDB file that we've just downloaded. And then we're going to replace the ligand files, the smile strings in the ligand text file, with our own. So here you'll see we've got the zinc ID now and the smiles, and this is from the combinatorial library building video. So you can see our list of about 30,000 molecules based on one-step reactions. And for the purposes of this video, I'm just going to virtually screen 100 ligands, just for the sake of time. Obviously, we could screen all 30,000 if we wanted to. However, given that PocketVina will screen each of these ligands against the highest ranked pockets, so multiple pockets on the protein, that will take a little while. So for purposes of this video, I'm just going to screen 100 ligands at once. And yeah, once we've done that, you can just run PocketVina here, and just remember to make sure that the protein path and the smiles file path point towards your ligand text file and your protein files text file. And then once you run the cell, PocketVina will start to run, and it will start to generate 3D conformers of the ligands from the smiles and put those into batches, so they'll be converted from smiles to PDBQT files, and then they will be dispatched into batches, and then P2 rank will start to detect the pockets on the protein's solvent accessibility surface. And you can check that your files are being saved as they're generated by going into your Google Drive and just checking and being able to see the output files, both the JSON and the PDBQT files. So the JSON files will contain information like the binding affinity, the RMS DB, and the JSON file will contain information like the docking score and the name of the ligand. And if you go into the folder labeled proteins and then into the pockets directory, you'll see a file called pureprotein.csv. And if you open that up, you will see each of the names of the pockets, their rank, their score, their ligand probability, solvent accessible points, coordinates, residue IDs, and also surface atom IDs. So there's a lot of useful information in there, defining those pockets for reference later. And then finally, once the docking has finished, you should be able to go into a folder called combined results.csv and be able to see both the protein pocket name, the molecule name, which is the zinc ID for the reagent, and the binding affinity in kilocalories per mole. And it will also give you the binding mode as well. And all of this information will be in the JSON file for that corresponding PDB Qt file. So they'll be stored together in each of the file batches. Okay. Now, once the virtual screen has finished running, in the results folder, you will find a file titled combined results as a CSV file. And if you open that, you will find the pocket name, molecule, zinc ID, binding affinity, ranked, and you can arrange those by order. So you can click on the affinity column and you can arrange them by binding affinity from highest to lowest. And obviously that file will also be saved to your Google Drive. And say if you wanted to find a file, you could just copy the zinc ID for that ligand and for that pose, and you could paste it into this search query widget. And if you copy and paste it into the text box and press play, it will search the directory for any files containing that zinc ID. And based on that zinc ID and the pocket rank, you will be able to find the PDBQT file and JSON file for that ligand with that score, so you could visually inspect it. And once you've located your PDBQT file, then you can go and visualize that docking flow. So you can first of all install Py3Dmol in your Colab instance, and then just input your receptor, which will be your original PDB file, and then your ligand PDBQT file, which you would have just found from searching via the zinc ID. And then once you run that cell, you will generate a interactive image, a 3D model of your protein and your ligand PDBQT file, and that will contain all of the poses for that particular ligand in that pocket. And they will be colored, so the lowest energy will be green and the highest energy will be red, so green being the best, red being the worst. And you can scroll through those and check the binding mode. You can download those from your drive or from Colab, and you can view them in other software like PyMol. And then lastly, the main advantage of us doing this in Colab using Python, other than the fact that it's obviously free, is that you can use Python scripts or R scripts to run data analysis of your ligands. So you can fetch the ligands from Google Drive and you can do some data analysis. So for example, you can plot a bar chart of the distribution of affinities versus their frequency. So you can see how many ligands score highly and how many score poorly and what the distribution is. So you can see that the most frequent binding score is about -6 kilocalories per mole, and there is very, very few ligands scoring -8.5 or below. And another example here is that you could you can plot the pocket rank versus the mean binding affinity. So you can see from this graph what pockets are more likely to have a larger number of better scoring ligands. So in this case, there's a slight misalignment on this chart, so the purple should be pocket 1 and then 2, then 3, etc. So we can see that pockets 1 and 3 are giving quite a large number of high scoring ligands, whereas pocket 5 has a much lower number of high scoring ligands, so on average. So that suggests to you that pockets 1 and 3 are probably worth investigating further, and pocket 5 most likely isn't. Okay, so that's everything for this video, and I hope it's been helpful.